This video is for section 9-2, real numbers as exponents. In the last section, we discussed rational exponents, exponents that are fractions. In this section, let's discuss real numbers, exponents which can be anything that's a real number. Consider this general function, y equals b to the x, where b is whatever number the base is. If the base is greater than 1, then we know the following things about the graph. It will continuously rise as x increases. We say that that increases from left to right, or rises from left to right. You see that when you look at the drawing, this green curve getting higher as you move to the right. Another thing we know about that graph is the y-intercept is 0, 1. It's touching the y-axis at 1. And that will be true for any equation that has this form to it. And one more thing we notice is the x-axis is an asymptote line. Look how the left end of the graph gets really, really close to the x-axis, but doesn't ever touch it. Now, what would this look like if the base was a number that was between 0 and 1, meaning some kind of fraction? This time, the graph falls as x increases. So as you travel to the right, notice it's going downwards. The y-intercept is still 0, 1, and the x-axis is still an asymptote to the curve. As you move to the right, this end gets closer and closer to the x-axis, but never actually touches it. Now, how do you actually create graphs like this when you have an equation with this format? Well, you use the same technique we've done for all our graphs. Make an XY table. So here's an example. Let's graph y equals 5 to the x power. This is called an exponential because the variable x is an exponent. One good number to choose is 0. And the reason that's a good choice is because it's easy to evaluate. What is 5 to the 0 power? Well, any number other than 0 to the 0 power makes 1. And that's why we said earlier that 0, 1 is going to be a dot on the graph. That's called the y-intercept. Now, what's another nice number to use for x? How about using 1? 5 to the first power. That makes 5. So 1, 5 is a dot on the graph. Now another nice number to use for x would be 2, because that would be 5 to the second power, which is 25. Now I left one row here so that we could try a negative number. How about -1? What is 5 to the -1 power? Well, think about the meaning of a negative exponent. It means reciprocal. This makes 1 over 5 to the first, or 1/5. We can find more dots if we need them, but with these 4 rows, we can make our curve. Before we actually plot the marks, I want you to notice that the grid that's on the paper is counting by 2's. So when it says -1, we're only going this far to the left. And then 1/5 is just a tiny bit above the x-axis. Now, 0, 1 is right here. Again, it's not this right here because this is actually 2, because it's counting by 2's going up. So this dot right here is 0, 1. Now, 1, 5. So over to 1 and then up to 5. That's right there. And then 2, 25. So over to 2 and then up to 25. That's right there, because halfway between 20 and 30 is where 25 is. With those dots, we can draw our graph. It's asymptotal to the x-axis, so right alongside the x-axis, and then curve it up through those dots. And put an arrowhead to show it continues forever. We can see that this has very quick growth to it. The exponential function y equals 5 to the x power starts out very flat, but once you reach positive x values, it swings up and increases very quickly. Next one. Let's look at an exponential function where the base is a fraction between 0 and 1. We already discussed how this would decrease from left to right. And on the front page of the notes, we saw that the general shape was a curve coming downhill like this. Now let's make an accurate graph on this grid. Again, choose 0 as one of your x values. 1/3 to the 0 power makes 1, and 1 take away 2 is -1. And let's choose 1 as well for x. 1/3 to the first power is 1/3, and 1/3 minus 2 is -1 and 2/3. If we want to extend the table, we could try x is 2 or x is 3 and so on. But let's not forget the negative numbers. So let's use x as -1. 1/3 to the -1 means a reciprocal, so it becomes 3. And 3 minus 2 makes 1. And let's use -2 for x. 1/3 to the -2 means the same thing as 3 to the 2, which is 9. And then 9 minus 2 makes 7. If we want even more numbers, we could choose -3 for x. But with these dots, we could probably get the graph. This time, notice the grid is counting by ones. So -2, 7 is left 2 up to the 7. The spot right here is 7. -1, 1 is left 1 up 1. Here's where 1 is. Then we have 0, -1. That's located right here. And then we have 1, -1 and 2/3. So over 1, down 1, and an extra 2/3. From these dots, we can probably draw the shape. But you know how it levels off along an asymptote line? This time, the asymptote line is not the x-axis. I mean, we can see that there are dots that are under the x-axis. So where does it start to flatten out? Well, that appears to happen at the -2. And in the equation, notice how that there is a -2 on the very end of it. So to show that asymptote line, since it's not the x-axis, you draw a dashed line crossing the y at -2. By drawing that dashed line, it gives you something to draw your curve alongside. Let's draw in our graph. Going through the dots, and then as soon as you get down to this area and you start to get to the positive x values, it starts to level off. And it's going to go right alongside that dashed line without ever touching it. There's our curve. Besides graphs, this section also reviews simplifying expressions and solving equations. So here are two examples of this. For the first example, we have a division problem involving powers. The exponent rule that we learned in an earlier chapter this year is to divide powers with the same base, subtract the exponents. Well, that rule is great, but that's about dividing powers with the same base. This base is 2 and this base is 8. So the new twist on it in this chapter is to rewrite these so they have the same base. The first one we can keep the same. But for the second one, let's rewrite the number 8 using a base of 2. Hopefully you agree that 8 is 2 to the third power. And that that number, which remember is 8, is raised to the square root of 3 power. This right here is equivalent to this here. Next, let's apply the rule about a power to a power is when you times the exponents. So we have 2 to the square root of 27 divided by 2 to the 3 square root of 3. Now we have powers with the same base. We can apply the rule. Keep the base and subtract the exponents. Is this first square root going to simplify? Well, it does. Think of the square root of 27 as the square root of 9 times 3. And what is the square root of 9? It's just a 3. So this is 2 to the 3 square root of 3 minus 3 square root of 3. You see what happens in those exponents? It becomes 2 to the 0, which is just equal to 1. So a problem that at the beginning seemed like it would make a pretty hard answer actually just turns out to equal 1. For the second example, it's not simplifying. It's an equation and we're asked to solve for k. But k is in the exponent, so we need a way to work with the exponents. And the key to doing that is again to make the same base. 8 is the same as 2 to the 3rd power. So this expression right here is equivalent to this one. Now over here, how can you write 16 using a base of 2? It's 2 to the 4th power. So this expression is really the same thing as this one. Now let's use that rule about a power to a power is when you multiply the exponents. So 3 times k is 3k, and 3 times negative 1 is negative 3. Now on this side, multiply those two exponents. It makes 12k. We have an equation, and both sides have the same base. So what must be true about the exponents? They have to be equal. So we can say that 3k minus 3 is equal to 12k. I'm taking the exponent on the left side and saying that it's equal to the exponent on the right side. But I only did that when I had the same bases. Now solve this equation. If you subtract 3k from both sides, you get negative 3 equals 9k. And then divide by 9 on both sides, you get negative 3 over 9 is equal to k. This does reduce, so negative 1/3 is equal to k. For both of these questions, the key to doing it was to rewrite them so that they used the same base. Let's summarize the lesson. The first thing we looked at is the skill of graphing exponentials. We tried an example of exponential where the base was a number greater than 1, and it made a curve that increased. We also did an example where the base was a fraction between 0 and 1, and this time the curve decreased. In that second example, we even had an asymptote line that wasn't the x-axis, and that was caused by that -2 on the end of the whole thing. Other part of this lesson was about rewriting expressions so that they have the same base, because that allows you to simplify and it allows you to solve equations.